A scroll compressor is a device for compressing air or refrigerant. It is used in air conditioning equipment, as an automobile's supercharger and as a vacuum pump. A scroll compressor operating in reverse is known as a scroll expander, and can be used to generate mechanical work from the expansion of a fluid, compressed air or gas. Many residential central heat pump and air conditioning systems and a few automotive air conditioning systems employ a scroll compressor instead of the more traditional rotary, reciprocating, and wobble-plate compressors. History: La copyright on Cray first patented a scroll compressor in 1905 in France and the US. Cray invented the compressor as a rotary steam engine concept, but the metal casting technology of the period was not sufficiently advanced to construct a working prototype, since a scroll compressor demands very tight tolerances to function effectively. The first practical scroll compressors did not appear on the market until after World War II, when higher precision machine tools enabled their construction. They were not commercially produced for air conditioning until the early 1980s. Design: a scroll compressor uses two interleaving scrolls to pump, compress or pressurize fluids such as liquids and gases. The vane geometry may be involute, Archimedean spiral, or hybrid curves. Often, one of the scrolls is fixed, while the other orbits eccentrically without rotating, thereby trapping and pumping or compressing pockets of fluid between the scrolls. Another method for producing the compression motion is co-rotating the scrolls, in synchronous motion, but with offset centers of rotation. The relative motion is the same as if one were orbiting. Another variation is with flexible tubing where the Archimedean spiral acts as a peristaltic pump, which operates on much the same principle as a toothpaste tube. They have casings filled with lubricant to prevent abrasion of the exterior of the pump tube and to aid in the dissipation of heat, and use reinforced tubes, often called hoses. This class of pump is often called a hose pumper. Since there are no moving parts in contact with the fluid, peristaltic pumps are inexpensive to manufacture. Their lack of valves, seals and glands makes them comparatively inexpensive to maintain, and the hose or tube is a low-cost maintenance item compared to other pump types. Applications: air conditioner compressor, vacuum pump, superchargers for automobile applications, for example Volkswagen's G-Leder. Engineering comparison to other pumps. These devices are known for operating more smoothly, quietly, and reliably than conventional compressors in some applications. Unlike pistons, the orbiting scroller unregistered trademark S mass can be perfectly counterbalanced, with simple masses, to minimize vibration. The scroller unregistered trademark S gas processes are more continuous. Additionally, a lack of dead space gives an increased volumetric efficiency. Rotations and pulse flow equals. The compression process occurs over approximately 2 to 2½ rotations of the crankshaft, compared to 1 rotation for rotary compressors, and 1/2 rotation for reciprocating compressors. The scroll discharge and suction processes occur for a full rotation, compared to less than a half rotation for the reciprocating suction process, and less than a quarter rotation for the reciprocating discharge process. Reciprocating compressor have multiple cylinders, while scroll compressors only have one compression element. The presence of multiple cylinders in reciprocating compressors reduces suction and discharge pulsations. Therefore, it is difficult to state whether scroll compressors have lower pulsation levels than reciprocating compressors, as has often been claimed by some suppliers of scroll compressors. The more steady flow yields lower gas pulsations, lower sound and lower vibration of attached piping, while having no influence on the compressor operating efficiency. Valves. Scroll compressors never have a suction valve, but depending on the application may or may not have a discharge valve. The use of a dynamic discharge valve is more prominent in high-pressure ratio applications, typical of refrigeration. Typically, an air conditioning scroll does not have a dynamic discharge valve. The use of a dynamic discharge valve improves scroll compressor efficiency over a wide range of operating conditions, when the operating pressure ratio is well above the built-in pressure ratio of the compressors. If the compressor is designed to operate near a single operating point, then the scroll compressor can actually gain efficiency around this point if there is no dynamic discharge valve present. Efficiency equals, the isentropic efficiency of scroll compressors is slightly higher than that of a typical reciprocating compressor when the compressor is designed to operate near one selected rating point. The scroll compressors are more efficient in this case because they do not have a dynamic discharge valve that introduces additional throttling losses. However, the efficiency of a scroll compressor that does not have a discharge valve begins to decrease as compared to the reciprocating compressor at higher pressure ratio operation. This is a result of undercompression losses that occur at high pressure ratio operation of the positive displacement compressors that do not have a dynamic discharge valve. The scroll compression process is nearly 100% volumetrically efficient in pumping the trapped fluid. The suction process creates its own volume, separate from the compression and discharge processes further inside. By comparison, reciprocating compressors leave a small amount of compressed gas in the cylinder, because it is not practical for the piston to touch the head or valve plate. That remnant gas from the last cycle then occupies space intended for suction gas. The reduction in capacity depends on the suction and discharge pressures, with greater reductions occurring at higher ratios of discharge to suction pressures. Reliability: scroll compressors have fewer moving parts than reciprocating compressors, which, theoretically, should improve reliability. According to Emerson Climate Technologies, manufacturer of Copeland scroll compressors have 70% fewer moving parts than conventional reciprocating compressors. In 2006, a major manufacturer of food service equipment, Stowelting, chose to change the design of one of their soft-serve ice cream machines from reciprocating to scroll compressor. They found through testing that the scroll compressor design delivered better reliability and energy efficiency in operation. However, many refrigeration applications rely on reciprocating compressors, which appear to be more reliable in these applications than scroll compressors. These applications include supermarket refrigeration and truck-trailer applications. Vulnerabilities: scroll compressors are more vulnerable to introduce debris, as any debris need to pass through at least two closed compression pockets. The scrolls that operate without radial and or axial compliance are even more prone to the damage caused by foreign objects. However, scrolls do not have suction valves, which is one of the most vulnerable parts of the reciprocating compressor to liquid flooding. Scroll compressors utilize different methods of protection inside the compressor to handle difficult situations. Some scroll designs utilize valves at different points in the compression process to relieve pressure inside the compression elements. A reciprocating compressor can run in either direction and still function properly, whereas a scroll compressor must rotate in one direction only in order to function. This can be important during extremely short periods of power loss when a scroll compressor may be forced to run backward from the pressure in the discharge line. Only single-phase scroll compressors would continue to run in reverse after the power comes back on. If this happens, the scroll compressor will stop pumping. Running scroll compressor in reverse for several minutes would normally not damage the compressor. The three-phase compressor, as compared to single-phase compressors, would revert to operation in a forward direction at the end of a short power interruption. However, it is important to properly wire the three-phase compressor during the initial installation. If during the installation the polarity is inadvertently reversed, then the three-phase compressor would run backward and the damage to the compressor may result if it goes unnoticed for a long period of time. Interestingly, one of the ways to mitigate the flooded operation of the compressor on startup is to actually run the compressor for several minutes in the reverse direction before turning the compressor in the forward direction. The short reverse run on the startup would expel any liquid accumulated inside the compressor pumping element back into the crankcase, as well as preheat the liquid stored in the crankcase by dissipated motor heat. Expelling the liquid from the pumping element and preheating any liquid refrigerant in the crankcase prior to initiating the normal run in the forward direction significantly alleviates problems with a flooded start. Size: scroll compressors tend to be very compact and smooth running and so do not require spring suspension. This allows them to have very small shell enclosures, which reduces overall cost but also results in smaller free volume. This is a weakness in terms of liquid handling. Their corresponding strength is in the lack of suction valves, which moves the most probable point of failure to the drive system, which may be made somewhat stronger. Thus the scroll mechanism is itself more tolerant of liquid ingestion, but at the same time is more prone to experience it in operation. Small size of a scroll compressor and quiet operation allows for the unit to be built into high power density computers, like IBM mainframes. Scroll compressors also simplify the piping design, since they require no external connection for the primary coolant. Partial loading: until recently, a powered scroll compressor could only operate at full capacity. Modulation of the capacity was accomplished outside the scroll set. In order to achieve part loads, engineers would bypass refrigerant from intermediate compression pocket back to suction, vary motor speed, or provide multiple compressors and stage them on and off in sequence. Each of these methods has drawbacks. Bypass short-circuits the normal refrigeration cycle and allows some of the partially compressed gas to return to the compressor suction without doing any useful work. This practice reduces overall system efficiency. A two-speed motor requires more electrical connections and switching, adding cost, and may have to stop to switch. A variable speed motor requires an additional device to supply electrical power throughout the desired frequency range. Also, variable frequency drive associated with variable speed compressor has its own electrical losses, and is a source of additional significant cost and often is an additional reliability concern. Compressor cycling requires more compressors and can be costly. In addition, some compressors in the system may have to be very small in order to control process temperature accurately. Recently, scroll compressors have been manufactured that provide part load capacity within a single compressor. These compressors change capacity while running. Reciprocating compressors often have better unloading capabilities than scroll compressors. Reciprocating compressors operate efficiently in unloaded mode when flow to some of the cylinders is completely cut off by internal solenoid valves. Two-stage reciprocating compressors are also well suited for vapor injection when partially expanded flow is injected between the first and second compression stages for increased capacity and improved efficiency. While scroll compressors can also rely on vapor injection to vary the capacity, their vapor injection operation is not as efficient as for the case of reciprocating compressors. This inefficiency is caused by continuously changing volume of the scroll compressor compression pocket during the vapor injection process. As the volume is continuously being changed, the pressure within the compression pocket is also continuously changing, which adds inefficiency to the vapor injection process. In case of a two-stage reciprocating compressor, the vapor injection takes place between the two stages, where there is no changing volume. Both scroll and reciprocating compressors can be unloaded from mid-stage compression, however reciprocating compressors are also more efficient for this mode of unloading than scroll compressors, because the unloaded port dimensions in case of scroll is limited by the internal port size, which would not be the case for a reciprocating compressor where unloading again occurs from between the two stages. Emerson manufactures a scroll compressor that is capable of varying the refrigerant flow as per requirement. Instead of fixing the scrolls together permanently, the scrolls are allowed to move apart periodically. As the scrolls move apart, the motor continues to turn, but the scrolls lose the ability to compress refrigerant, thus motor power is reduced when the scroll compressor is not pumping. By alternating the two different working states, the loaded state and the unloaded state, a solenoid contracts and expands the rotating scroll and/or the fixed scroll, using axial compliance. The controller modifies the load time, and the unload time, matching the capacity of the compressor to the load requested. This type of scroll compressors, while offering variable capacity control, normally down to 20% of the full flow, can suffer from a significant loss of efficiency, especially toward the lower range of the capacity control. See also, vacuum pump, gas compressor, pump, compressed air battery. References. External links: Copeland Compressors 111, video showing how the scroll compressor works.